Hello, good morning to everyone. This is the first seminar of the Spotlight Seminars on AI series. And today we are very pleased to have with us Moshe Vardi. And I would like to ask Giuseppe Giacomo to introduce our distinguished speaker.
Thank you. It is a great pleasure for me to introduce our speaker today, Moshe Vardi. Moshe is a George Distinguished Service Professor in Computational Engineering at Rice University, Houston, Texas, and is one of the most prominent theoretical computer scientists in the whole history of the discipline. Moshe provided a number of fundamental contributions in very many areas of computer science, including formal methods, database theory, automated reasoning, automata, logic in computer science, and final model theory. The excellence and the relevance of his scientific accomplishments are testified by the impressive number of recognition and awards. Among them, three quite diverse ACM awards: the Kurt Gödel Prize, the Paris Kanellakis Award for Theory and Practice, and the Sigmod Code Innovation Award. Each one from a very different community of ACM, confirming the excellence but also the variety of the research activity of Moshe. Moshe has also been invited to give keynote talks in very prestigious conferences in AI, in databases, theoretical computer science, including EJKI, AAAI, EKI, KR, PODS, LEAKS, ICDT, ICAP, ICLP. Moshe's contributions, however, are not limited only to scientific achievement. For example, he has been the editor-in-chief of communication of ACM. And when he started the job in 2008, the journal was somehow in a deep crisis, and he has done a fantastic job to actually revitalizing the journal and making a real flagship publication of ACM. Also, possibly since then, Moshe has become interested in the social aspect of our disciplines, especially related to the impact of automation in the job market, ethical issues in computer science and artificial intelligence, resilience in computer science, artificial intelligence, and more generally in all science of artificial. And I suggest everybody to watch some of the videos of his talks on YouTube on these issues. They are very informative, interesting, and enjoyable. I personally had the privilege to work with Moshe when I met him at ESLI 1998. I invited him for a workshop, and then we start talking about rewriting of regular path queries. Okay, regular path queries, and since then we've been working together on very many issues related to logic, computer science, and AI, planning, program synthesis, graph databases, Open API, and more. And working with him is a wonderful experience. You benefit from his skills and his vast, deep knowledge, but also you have the possibility of enjoying an infinite number of stories, anecdotes, jokes that he tells all the time. So you surely will not get bored. Okay, so let me finish this introduction by thanking Moshe to be here and accepting our invitation, and giving him the floor for his talk entitled Machine Learning and Logic, Fast and Slow Thinking. Moshe, the floor is yours.
Thank you. Buonasera. Grazie mille. Thank you for the opportunity to address you, and thank you, Giuseppe, for this such very kind introduction. Clearly, things have changed drastically in computer science over the past few years. And to me, one of the signals for that by now, about 80% of our incoming PhD students, when they write in application, what do they want to do? They want to do AI. So I look at my webpage, and it said that I do logic in computer science. So now I decided, okay, time to change my webpage. And I said, I do automated reasoning, which is a branch of AI. So, but when people say AI, very often today, they mean machine learning. And the people who do what was it called? Plain old-fashioned AI. That people still do like symbolic reasoning. Wow, you're still doing symbolic reasoning? What's wrong with you? So that's what I want to talk about this tension between kind of symbolic AI and machine learning. And I want to show that there are really two sides of the same coin. Okay, now I have to. Okay. So the perception is there is a famous book that came, I think, in 1960 by Thomas Kuhn, The Structure of Scientific Revolutions, and he introduced the phrase paradigm shift, and he said certain time there is standard science and there is revolutionary periods where there is a paradigm shift. We did classical physics, and then we had the general relativity, and there was a paradigm shift. And then when quantum mechanics, it's another paradigm shift. And now all we hear all the time is machine learning, big data, data science. And there is a sense that we went from having like formal model to just being data driven. And there's a paradigm shift, and you can throw out all the old stuff, and nobody needs to know any of the old computer science. Everything is just going to be machine learning, or even not just that, deep learning, deep reinforcement learning, nothing else is needed. But if you talk to a philosopher or historian of science, they will tell you that this paradigm shift has been greatly exaggerated, in the sense that yes, sometimes we really totally abandon, like we abandoned the Ptolemaic model of planetary moves. We adopted the Keplerian, the Copernican, Keplerian, ultimate Newtonian model. But just because we have general relativity doesn't mean we abandon Newtonian mechanics. How did we go to the moon? When you send a rocket to the moon, there are no relativistic effects. You just use Newtonian mechanics, that's it. So the way to think about it, and I heard it from Steven Weinberg, who's a Nobel Prize in physics. He said that the new theories refine the old one. They usually don't throw them out, they refine them. And that's what I want to argue, is that data science refine formal science, formal models. It doesn't throw it away. And we need to figure out how the two live together. And to understand how the two live together, I need to master slides here. Okay. I want to bring the paradigm of fast and slow thinking that has been popularized by Daniel Kahneman in a famous book, 2011, Thinking Fast and Slow. And he basically says that our intelligence has two parts. We have the aft brain, the lizard brain, we call it sometimes, and the forebrain. And one is fast thinking. So if you are walking the savannah of Africa, and you see something yellow moving in the grass, in the tall grass, you need very quickly to identify, to decide that this is risky, that this might be a lion, and you need to get out of there. And you don't have time to go and collect data, and you have whatever data you have, you decide, is this a lion or not? So this is fast thinking, and we do it all the time. You see a snake, you recoil. You don't start analyzing, is it poisonous, is it not poisonous? First, you recoil. In modern term, if you're building autonomous vehicle, is this a stop sign, or what kind of sign is it? You need very quickly to recognize signs. This is fast thinking. And this is where machine learning is now doing an outstanding job. But we also need, going back to the savannah, if you made it alive back to your village, you want to tell people there's a lion out there, let's go hunt the lion. And you're going to come up with a plan how to hunt the lion. This is slow thinking. This is what we do with the forebrain, not with the lizard brain. And that's where logic comes in. Logic is, do I need to stop at the stop sign? And in some sense, you can think that machine learning is just about pattern recognition in some sense, and logic is trying to go deeper into the semantic of the situation. And I was very much influenced by a paper written in 2017 by Amnon Shashua. Amnon Shashua was a professor of machine vision at Hebrew University in Jerusalem, and he founded a company called Mobileye, and then Intel bought it for billions of dollars. And so he's written a paper about how can we guarantee safety of AVs? And he first make an argument that AV need to be about 1,000 times safer than not 10 times safer, 1,000 times safer than what we have with human-driven vehicles. Because he said, if United States, if 50,000 people die from car crashes every year, if we'll have 5,000 fatal car crashes with AVs, people will not accept it. So he said, if you're going to be just data-driven, you'll have to drive 1 billion miles to be able to train enough to reach this level of safety. But he showed that if you take data-driven analysis with also models of how the car operates and how it can fail and how crashes happen, then you can reduce by a factor of 1,000. You can bring it to million miles. Billion mile driving, billion mile test driving is not feasible. Million mile test driving is feasible. So I think kind of the grand challenge today for our community is to figure out how to combine logic with machine learning. We have two paradigms that need to work together. And that's something I've been focusing for the last few years. And I want to give another reason why we need to combine logic with machine learning. And this has to do with automated decision systems. So automated decision systems are now being more and more spread around us. You know, now you apply in the United States, if you apply, let's say, for a loan, for a mortgage, it's very likely the decision will be made by an automated decision system. More and more in the justice system, people are using automated decision systems. In 2018, Jim Larus and Chris Hankin wrote a column in CACM about regulating ADS, and they said the widespread adoption of AD system will be economically disruptive and will raise new and complex social challenges. Disdain for regulation, they write, is pervasive throughout the tech industry. In the case of automated decision making, this attitude is mistaken. Now, of course, the hard question is how to regulate it. What should we require? And we're talking about faith, fairness, accountability, transparency, in particular, explainability. We want decision by automated decision system to be explainable. Now, what does it mean to be explainable? So let's take something even very simple. I write recommendation letters. Every week I write one letter. So suppose I write a letter for promotion, I will write one sentence, and I will say, you know, I'm Moshe Vardi. I'm a very senior computer scientist. I recommend John Smith for promotion. No one will take this seriously. They would want to read an explanation. Every time I write a recommendation letter, I make a recommendation for a decision and I add an explanation. And the explanation has to be high level, has to be human level explanation. I can't say my recommendation neuron fired the recommend, so that's why I'm telling you this. That's useless. People want to hear a human level explanation. And language in which we can offer precise reasoning is the language of logic. And that's why we have another motivation to combine logic with machine learning. And some people talk about neurosymbolic reasoning. But as soon as you start doing it, you discover very quickly that kind of classical logic that was focused on true and false, qualitative, excluded middle, is too coarse. In real life, things are not black and white. In fact, this was kind of the big contribution. If you look at the waves of AI, first wave was, I would say, call it the McCarthyan wave, which was about symbolic logic. And the second wave, before we got into machine learning, was probabilistic reasoning, because Georgia Perel, are you convincing me that to reason about the real world, we need the concept of probability? And so my approach over the last decade is to try to make logic quantitative. So let's see what I mean by that. So let's kind of jump to a little background, a little bit on motivation about logic. So of course, logic goes back to all the way to the classical Greek, to Aristotle. But a huge jump, I mean, the beginning of mathematical logic goes back to George Boole, because George Boole took philosophy out of George Boole took logic out of philosophy and moved it to mathematics. And how did he do it? He realized that you can think you can think of logical reasoning algebraically. And you remember the 19th century, Boole's book is around the middle of the 19th century, where mathematicians discovered that many things that we started from numbers can reason about them abstractly. So we can take a multiplication, and we said, let's just focus on multiplication. Well, we define now, we have group theory for multiplication. You want multiplication and addition. We talk about fields, we talk about rings. So we start studying abstract algebraic structure. And Boole said, let's do the same thing for logic. And his big insight was that conjunction, logical conjunction, is really a multiplication operation. And logical disjunction is in some kind of an addition operation. And that's what gives rise ultimately to Boolean logic, Boolean algebras. That's why we talk about Boolean algebras. So that was a big jump. And then even Boole started thinking about reasoning. And there's a whole history here about reasoning, but it finally was in the 20th century, we focus more on the satisfiability problem, which is given a Boolean expression, building and or and not, is there a satisfying assignment? Is there a way to assign zeros and ones to the variable so the whole expression would comes out 1? Now in this case, we have 4 variables, and you can see very easily, just as I'm talking, if you take x1 and x2 to be 0, false, and x3 and x4 to be 1, the whole thing will evaluate to 1. But you have 4 variables, there are only 2 to the 4, which is 16 truth assignments. You can just check all of them very quickly and see that it is satisfiable. What will happen if there were 40 variables? Now 2 to the 40, wow, that's a much larger number. Suppose it's going to be 4,000 variables, or maybe even 400,000 variables in some application, maybe 4 million variables. Clearly, brute force search is not going to be effective here. So how do we do this kind of reasoning? And amazingly, the difficulty of Boolean reasoning is something that already emerged in the 19th century, before there was any complexity theory, before they were even people study formally algorithm, the runtime. William Stanley Gibbons was a follower of Boole. Right, I've given much attention, therefore, to lessening both the manual and the mental labor of the process of Boolean reasoning. I shall describe several devices which may be adopted for saving trouble and risk of mistake. And in fact, he builds the first logical machine in the 19th century. Ernest Schroeder, a German algebraic and logician, to me this is an amazing quote, writes, getting a handle on the consequences of any premises, or at least a fastest method for obtaining these consequences, seems to be one of the noblest, if not the ultimate goal of mathematics and logic. So he declared essentially Boolean reasoning is the ultimate goal of mathematics and logic. And there have been attempts to make progress on this. And ultimately, in the early 70s, Cook and Levine proved that Boolean satisfiability is NP complete, and therefore we think it's going to be a difficult problem. People work on it, so this is kind of the beginning also of complexity theory and NP completeness. On the other side, there have been attempts to develop algorithmic Boolean reasoning all the way to the mid-50s. Newell, Shaw, and Simon wrote a program called Logical Theorist, in which they did Boolean reasoning. And then a few years later, Davis and Putnam wrote an unpublished report for the National Security Agency, Computational Methods in the Propositional Calculus. A couple of years later, paper in JCM by Davis and Putnam, a computing procedure for quantification theory. And finally, another paper, 62, in CSCM, a machine program for theorem proving, David, Logman, and Loveland. And putting all these things together, you get what we have called for many years the DPLL method, which is really just a backtracking search, but you convert the formula to conjunctive normal form, which is what we have seen before. We've seen conjunctive normal form. You do a backtracking search, and there was just one heuristic, which is the unit clause preference, that if one of the clauses is a unit clause, just either it says P or it says not P, then there's nothing to branch. P has to be true or P has to be false. You make this assignment and you propagate it, and then you continue. So for many years, I would say from The next 30 years, DPLL is the dominant method, and it can solve by the early 90s. It can solve problems with few hundred of variables. And if you told the people who are working on this that this is not good enough, that we need to solve bigger problems, they would say, but it's a hard problem, it's NP complete. What do you expect us to do? And then in the mid 90s, we started what I have called the SAT revolution. And modern SAT solving start in a paper in 1996, and they have coined it as CDCL. I'll come back to this name, conflict-driven closed learning. And it's a collection of heuristic. These 5 heuristic together is what people call CDCL solvers. It involve not backtracking, but backtracking, you go one level up in the search tree, but you can be smarter and jump several levels up. So this is called back jumping. Unit clause is a very good heuristic, but the traditional way of implementing it using counters was actually had a large overhead. So people came up with very clever data structure to implement unit clause preference. CDCL meant that if you do a search and you fail, that means you discover one bad partial assignment, and you want to identify it and make sure that you don't repeat it in the future by adding another clause. So you learn new clauses that are going to prevent bad partial assignments. How to choose variable to split on is a very critical thing. I call it the Brainiac versus speed demon. You can have very, very good heuristic. They're very smart, but they're so smart that they slow you down. So it turned out it's better to have less smart heuristic as long as they are faster. And there's a concept of restart, which is sometimes you just decided this is a bad search tree. I'm going to just abandon the search, go back to the beginning and restart. But I have all the new clauses that I've learned during this failed search that will affect the next time I do that. And 2 very important tools that came out was GRASP in the mid 90s, and then 5 years later SHAF. And today we solve problem with millions of variables. Today it just, I say, we went in 25 years, or maybe 30 years, from hundreds of variables to millions of variables. And even a decade ago, Sanjit Seshia put this slide, which I liked very much. He wanted to solve the progress over 1 decade. So he took a 12-year worth of SAT solver, starting from GRASP in 2000, and took the same benchmark on the same machine. Naturally, because we're talking about over a decade, people running on different machines. He ran all of them on the same machine, and he showed how you got a speed up. You went from 800 seconds in 2000 with the 2000 solver to 1 second in 2012. So this has been such amazing progress that people are half jokingly refer to it as Moore laws for SAT solver. SAT solver are continuing to get better and better. And this even Don Knuth, kind of the closest we have in computer science to a patron saint, so to speak, and who is mid-80s, still in good health. In the coming flock, he's going to give one of the keynotes in the coming flock in early August. And in 2016, he received recognition from Science Society for Industrial and Applied Mathematics, and he gave the John von Neumann lecture and talked about satisfiability. Because he said this is an amazing progress, and in fact he showed that the mystical volume 4 that Don Knuth has been working all of his adult life on is by now divided into sub-volume. He called them fascicle, and one of the fascicles is all about satisfiability. And he described it. He said the story of satisfiability is the tale of a triumph of software engineering. Then it would read those of beautiful mathematics. I think he mean algorithmic engineering, not software engineering. Software engineering is more how to write good software. Here it's real algorithmic engineering, which is all the heuristic and all the cleverness that got into modern SAT solvers. And while, again, if you go back a few years ago, such solvers was purely an academic pursuit, today such solving is an industrial reality. And already a decade ago, Leonardo de Mura and Nicola Bjorner wrote how Z3, a such solver, is used in Microsoft, not Microsoft Research, in Microsoft, for software development, for symbolic execution, for model checking, for static analysis, for model-based design. So Microsoft has been very successful for doing tech transfer, taking technology outside of research into the product development unit. And it is now part of the process of software development at Microsoft. I've been interested a big part of my career in verification, mostly of hardware and software system protocols, semiconductor design, and this is a huge industry. I mean, I wrote this slide a couple of years ago. It was $750 billion per year. Today it's probably $1 trillion a year. And it turned out when you develop systems, it is well known that 70 to 80% of your design cycle go into verification. You design the system and then you discover it has bug, you have to debug it, you have to redesign it. This is a hugely expensive operation. So now my focus has been almost for most of my career on formal verification. On essentially, you look at mathematical models and you prove mathematical properties of this mathematical model. Mostly I was focusing on model checking. But when you talk to companies who use model checking and you try to quantify how much they use it, you say, okay, you have a verification team. How many people in the verification team are doing formal verification? This is not purely scientific. This is kind of somewhat semi-scientific. I've asked many people, and my estimate is always it comes to less than 10% of the verification effort is formal. Just by asking, okay, you have 40 people, how many of them do formal? And it's usually a small team. What do the rest of the people do? They do what the industry called dynamic verification, or in software it is called testing. You simulate your system under different testing scenarios. You compare the result to the desired result, and this is what you call people sometimes call it verification or validation, and this is more than 90% of verification effort. So dynamic verification today is the dominant approach. As much as we've had great success with formal verification, and we had I think several Turing Awards went to people who made contribution in formal verification. The most recent ones, Clark, Emerson, and Sisler for model checking. The dominant approach is dynamic verification. You simulate the design with input test vectors. That's what I call test vectors. And this test vector represent different verification scenario. You compare the result to the intended result. And if they don't agree, then you discover a problem. Then you have to analyze the problem, but that's a whole other story. Of course, the problem is that the test space is incredibly large. Okay, it's very, very, very large. We have no hope of covering the test space in full. Take something very simple, floating point error. You may remember mid-90s, Intel had a floating point error in the Pentium chip. It was hugely embarrassing. They had to recall the Pentium. It cost them hundreds of millions of dollars. It was very expensive. So how do you make sure that, and bidding today, floating point divider is highly non-trivial. So what are we going to do? How are we going to test it? So clearly we cannot test all possibilities. If you have two numbers, which are 128 floating point number with 128 bit floating point numbers, you have 256 possibilities. This is such a humongous number. Even if you have the fastest possible computer, the sun will go nova before we are done. So we need to do something more scalable. So the way people did it, you had verification engineer who wrote tests, and every test they would read the specification, they would read bug reports, they would read field test reports, and that's how they would write tests. Every test was like writing code. And the conventional wisdom is that a software engineer can write about 20 lines of code per day. So a verifier can write 20 test cases per day. So if you have a team of 100 people, they write 2,000 test cases per day. That's still very, very small number. So by the mid-90s, people realized that this is also not scalable. And Liechtenstein, Malka, and Aharon in IBM Haifa in Israel came up with a very clever idea. The idea is that a scenario should be described not by a specific test vector, by constraint describing a possible scenario. Now you send this constraint to constraint solver. The constraint solver give you different solutions, and these are your test vectors. So now you can have, for each scenario, you can try many different test cases by running the solver again and again and again and again. But we don't want just to give you what the solver give you, depending on internal of the solver. You should generate ideally what you would like to do is to generate a solution randomly and uniformly. Why randomly? Because we shouldn't depend on the internal of the solver. And why uniformly? Because if we have no idea where the bug may be, our best search strategy was to search uniformly. And you can now take it down very simply. You say, suppose I'm giving a Boolean formula. I don't want just to know is it satisfiable. I want to generate solution uniformly at random while scaling to industrial size problem. And I heard of this problem in 2006 when I heard a talk given by someone from IBM Research. And I thought, wow, this is a beautiful theoretical question. First of all, suppose you have a such solver. How do you turn it into a sampler? Something that would generate, or we call it UniGen. How do you generate uniform generation of satisfying assignment? So you take a black box, which is a such solver, but use it to generate random solutions uniformly. So this is the problem that I discovered in 2006. And it turned out that this problem has many applications. We saw it for consent random test generation. There are other, it's used in probabilistic inference. You want to sample after conditioning. If you want to try to do search-based optimization, you want to generate random points to see what the optimal value may be. And one of the coolest application is personalized learning. You have a MOOC and you want to generate assignments, homework assignments, but you can give 100,000 students the same assignment because somebody will post a solution on a discussion forum. So you want to generate 100,000 different problems. How do you do that? You define constraints on the parameter space, and then you generate instances uniformly at random. It turned out that this is the classical problem in theoretical and computer science, and people have been studying it starting from the mid 80s. And the first it was by Jerome, Valiant, and Vazirani, and they showed that is in so-called sigma. So you have a randomized polytime algorithm with a sigma P2 oracle, second level of the polynomial hierarchy. And then a few years later, this was improved by Bellari, Goldreich, and Petrank. And this is a beautiful result. They show you can do uniform generation of NP witnesses using an NP oracle. What is NP oracle? For example, a such solver is an NP oracle. So I got interested in this problem, and I started working with a student on this in around 2011. And so the first thing I told him, why don't you go ahead and implement the Bellari, Goldreich, and Petrank algorithm. We call it the BPG algorithm. A BGP, it's a type of BGP algorithm. And so he did, but we couldn't scale it beyond 16 variable. After 16 variable, it would just never finish. Never, 24 hours. It wouldn't finish in 24 hours. So the student was still excited about what he did. He wanted to, and I said, this is not publishable. He said, why not? I said, look, people are now solving such instances with hundreds of thousands of variables. We will go there, we'll try to submit a paper with 16 variables. They wouldn't just reject it. They would laugh at us. I told him then, we have to bring at least to 1,000 variables, otherwise it's not publishable. Now we look what other approaches are to do this, more practical approaches to do this. And we found other approaches that people are using. One was you build a BDD, and then you take a random walk on the BDD. And that gives you, again, uniform solutions at random. But BDD rarely scale beyond 1,000 variables. After you have about 1,000 variables, even below that, maybe 800 variables, the BDD gets too large and it doesn't fit into memory. You have to start, putting it on disk, and everything slows down to a halt. So again, about 1,000 variables, not more than that. Now, so what do people do in the AI world? We discover in the AI world, people use MCMC-based algorithm. That's the dominant approach. The problem with MCMC is they're scalable, but we know that really to get uniform distribution, you have to go to the limit, and you get to the stationary distribution of the Monte Carlo of the Markov chain, and it takes too long. So in practice, what people do, they run polynomial time, and then they start sampling. But then they get, it's not uniform, and in fact, you have no guarantee on how uniform it is. The other thing that you can do, you take your that's a SAT solver, you introduce many random steps. Then you get something, but people run experiment, and you see it is very, very non-random. You can kind of test it for randomness, and you see that just trying to randomize particular step inside the solver is a very poor way of trying to get uniformity at random at the output level. So we embarked on revisiting the theory. We went back to the theory and asked, how do we make the theory scalable? And we realized that to get uniform randomness, we couldn't do it better, but we could do a little compromise. And this is almost uniformity. And I'll explain what is almost uniformity. So now we have a randomized polynomial time algorithm. It uses SAT solver as an oracle, as a subroutine. In fact, it uses SMT solver. I'll talk about that in a minute. It uses universal hashing. I explain it. Then it can scale to millions of variables. And in fact, after you do some pre-processing, you can generate many samples in parallel, and they will be independent and almost uniform and random. So what is the key to doing this? So first, let's see what I mean by almost uniformity. So suppose you have a Boolean formula phi, and there's solution space, let's call it sol of phi. And suppose there are kappa solution. So what does uniform mean? Uniform means that each satisfying assignment has a probability of exactly 1 over kappa, because they're kappa satisfying assignments. So each satisfying assignment exactly 1 over kappa. And the answer is, how about we compromise a little bit? Give me some parameter epsilon, and I want the output probability for y to be within 1 plus epsilon multiplicative neighborhood of 1 over kappa. Maybe a little smaller or a little larger, but if you take kappa to be small enough, it should be fairly close to uniform. So, and you decide, of course, the smaller epsilon is going to be, the more you'll have to work. The ultimate case in this case, of course, will be epsilon is 0. That's going to be very expensive, but we can do almost uniformity and be principled about how close we are to uniformity. So what is the basic idea? The basic idea is to take the whole solution space and divide it into roughly equal small cell of appropriate size. What is appropriate size? I'll explain in a minute. You choose a random cell. You enumerate the solution because the number of solutions in each cell is not very large. So you enumerate them, and then you choose at random. And because the cells are roughly equal, they're close to being equal, you have almost uniformity. The question is, how do we take a solution space that we don't really understand? I write you a Boolean formula. What do you know about the solution space? It's some crazy space. How do I divide it? And I know nothing about the distribution of solutions. How do I divide into roughly small equal cells? And here you bring the idea of universal hashing. And again, it's an idea that go back to theoretical computer science, started in 1979. How do we use it? So hash function generally will map, let's say, bit vector, n bit vectors, to m bit vectors, where m is much smaller than n. And a good hash function says if you start with a very well, a good distribution, let's suppose you start with a uniform distribution on the input space, then the output space will also be uniformly distributed. All the cell, the collision will be about equal size. The problem is people realize that the input space is very non-uniform. Take, for example, we hash passwords. Everybody knows that the password that human people generate, human generated passwords, are very, very non-uniform. In fact, that's something that hackers very often use to try to break a password. That's why password is a relatively non-safe way of guaranteeing security. So the idea of universal family of hash function was a brilliant idea. So instead of assuming that the input space is random, let's randomize the hash function. So instead of having a single hash function, you have a family of hash functions, and you choose one at random. And the mathematical theory tells you if you start from arbitrary distribution of the input, if you choose the hash function randomly, then all the cells, all the value that are coalesced to one hash value, all the cells will be roughly equal in expectation. So with high probability, the cells will be roughly equal. Okay, this is the property that we need here. So it's a magical device. Okay, we need randomness, but instead of assuming it on inputs, let's randomize over the hash function. Now, it's not enough. What we need to do that is also to make sure that the hash function treats the space in a uniform way. It's not enough uniformly, but also we need independence, because we need to say if you do certain tests, you can repeat certain tests, for example, and the test will be independent. And for this, we need a level of independence. So there is a theory, and I won't go in great detail into it, but it's called R universality. So a family H, N, M, N and M were the parameter we saw before, and now we have a third parameter R. So these are hash function, and what you have to prove is that every R elements, if you take an arbitrary, if you choose at random R elements, they will be mapped independently. The outputs will not be correlated. If the inputs are not correlated, the outputs will not be correlated. And this is true up to R elements. Now, the higher R, you get strong guarantee on the distribution of the cells. So you want to have high R universality. And it is not hard to accomplish it. If you want R-wise universality, you need to use polynomial of degree R minus 1. So more universality, higher degree polynomial is going to cost you. Now, BGP wanted full uniformity, and that meant they needed n universality. And then all the cells are small, and you have uniform generation. We said, well, suppose we lower it. We don't require n universality, which is very expensive. Instead, we said, suppose we go to 3 universality. Then that was enough to show that a random cell is small with high probability. Not guarantee, but with high probability. And that gives us almost uniform generation. And that was the key to be able to go from tens of variable. Remember, with BGP, we got 16 variables. We couldn't scale it beyond 16. We got it to where we can handle millions of variables, which are industrial scale problems. Now, the other question is still the hashing here is a bit of a mystery. How do you do the hashing? So the answer is we do the hashing by using XOR constraints. So the goal is to partition the full input space 0, 1 to the power of n into 2 to the m cells. So if we have n Boolean variables, we're going to form XOR constraints by choosing each variable with probability half. Does it go into the constraints or not? And the value of the sum will be 0 or 1, again with probability half. So each such constraint split the solution space in half. And if you have m such constraints, you'll have 2 to the m cells. How many constraints do you need? That's part of the processing. We remember we want each cell to be relatively small, let's say with 100 solutions at most. So we have to do some experiment to figure out how many extra constraints we need. But now every cell is described by a combination of the original formula, which is CNF, and XOR constraints, XOR clauses we call them. How do we solve such problem? It's called CNF XOR. So it's very easy to take XOR and just convert it to CNF. That's an easy reduction. It's a undergraduate logic exercise to convert XOR to CNF. The problem is if you do that, you convert to CNF, you discover that such solvers, CDCL such solver, are doing a very poor job on solving XOR clauses. In fact, even if you just have XOR clauses, and if you only have XOR clauses, you can solve it efficiently using these are just linear equations modulo 2. So you can solve it using Gaussian elimination modulo 2. So we can solve it very efficiently. But if you ask such solver to solve XORs after conversion to CNF, it will perform miserably. So it turns out that Gaussian elimination is a really brilliant idea. And if you try to do search, it performs miserably. So how do we solve such problems? Here we get into SMT solving. So after the initial success in the late 90s of such solvers, of CDCL such solver, people say, well, let's leverage this success. Can we go to more expressive constraints? Can we combine Boolean constraints with linear constraints, with bit vector, with other type of constraints? And so SMT stands for satisfiability modulo theory. Let's add another theory on top of the Boolean theory. And tremendous progress has been made since 2000. And in particular, remember, we are talking now, we are in about 10 years ago. We are looking for something to solve CNF plus XORs. And we stumbled on a solver that was called CryptoMinisat that was developed by Matesus in 2009, published in 2009. And he was looking specifically at CNF plus XORs. And he combined such solving, CDCL such solving, with Gaussian elimination in a clever way. You can see from the name, he was interested in trying to reason about cryptographic protocols. And that proved to be very difficult because one of the things you do in cryptographic protocol is also to do multiplication. And multiplication, it is known that it's very hard to reason about multiplication. But the solver was sitting there waiting for us. And when we use it, it was very effective for the application that we needed. So we are able to get it to UniGen. And so let's see how well does UniGen perform. So one is, remember, it's almost uniform. It's not uniform. So how good is it? So we took a problem that has million solutions. So we can generate all solutions. And then we can implement a uniform sampler. Once we have a million solution, we can implement a uniform sampler. And then we run UniGen. And we saw how many, no, I think we don't, we saw how many, we ran it for many, many times. And we saw how many solutions, how many times each solution is being selected. And what you get, of course, is a bell curve. And you see that there is really no statistical difference between the green one, which is UniGen, and the uniform sampler. So even though we're doing only almost uniform sampling, in practice it is indistinguishable from uniform sampling. It gives us any statistical test of uniformity would say this is uniform. So this is good. This is the good news. Almost uniformity is acceptable. It's actually very good. The question then, how well does it perform? So we compare it to one of the best at the time, was the best of breed sampler that was available. It was called XOR sample prime. It was also based on using XOR constraints, but with a less well-developed theory that we had. And first of all, UniGen gave us almost uniform sampling. XOR sample prime just says best effort. I can't guarantee anything. And you can see that UniGen was faster by orders of magnitude. It was faster than XOR sample prime. So they had the right idea of using XOR sample prime, but we needed more theory and more algorithmic engineering to get it to have principal approximation and to perform well. Now, once we saw that we could do sampling, the next question was, can we use a similar technology to do counting? So counting is how many satisfying assignments do you have? And for example, if you just have P or Q, there are 3 satisfying assignments: 0, 1, 1, 0, and 1, 1. And this is called SharpSat, and it's complete for SharpP, which are the class of counting problem for decision problem NP. So NP is a decision problem. You can turn every NP problem into a counting problem. Ask how many accepting runs of a Turing machine, a non-deterministic Turing machine, how many accepting runs does it have? And this is the class SharpP, and SharpSat is SharpP complete. This is the theory developed in Valiant in 1979. And it turned out that constraint counting also had many applications. Go back to random consent verification. You would like to know, in this scenario that I have, how many consents are there? I would like to get some sense of how good is your coverage, what fraction of the scenario space have you covered by doing random sampling. But also in in Bayesian inference, you have a graphical model, and you have some inputs, and now you want to condition the probabilities that it can be shown, it can be reduced to consent counting. Planning with uncertainty, you have the same issue. You want to choose a plan that will be correct with high probability. So people have going back now more than 20 years, people have taken SAT solvers and tried to convert them into SAT counters. Instead of just finding the first truth assignment, try to count all satisfying assignment by being smart. But it turned out the SharpSat is a very hard problem. So even though we have no formal proof that Sharp is harder than NP, we have no proof of that. But in practice, SharpSat is much harder than SAT. So as I say, for SharpSat, for SAT we solve industrial problems today with millions of variables. But there's no way we can solve this problem for SharpSat. In fact, when we started, we looked at its industrial benchmarks. Existing SAT counters could not handle more than 50,000 variables. So we took the theory of approximate sampling to approximate counting. And again, the idea is we'll approximate it, but we want to do principal approximation. And the ideas of principal approximation, which is called PAC. It's probably approximately correct. It was introduced by Larry Stockmeyer. Valiant is well known for PAC learning, but he took the concept of PAC from Larry Stockmeyer. Larry said, let's look at any function that computes a value. How do you approximate it? So in this case, we want to count how many solutions we have. We have 2 parameters. One is accuracy. What kind of error are you willing to tolerate? Again, we want to approximate the count by a factor of 1 plus epsilon from above and below. But again, if we try to do it, we are willing to do it probabilistically, but then we want some degree of confidence. We want the confidence to be at least delta. So we have 2 parameters: how accurate you want to be and how confident you need to be. So this concept was introduced by Stockmeyer, and then it was studied for SharpSat by Jerome Sinclair and Valiant, and they showed it was in BPP to the NP. And in principle, it means that you can run a randomized polynomial time algorithm with the SAT solver as an oracle and implement it. We find no implementation, but we didn't even try to implement it because we were sure it was clear we were going to run the same problem that people have run previously. It was designed. It's a beautiful result designed by a theoretician, but it's very far. If you try to implement it, it's not going to run effectively. So again, we had to go and redo the theory in order to get something that would run effectively. And we use the same idea with XOR constraints. So remember, before that, we use M random XOR clauses to select a small cell and sample from it. Now we don't sample from it. We count how many solutions are in a cell, and multiply by 2 to the m, and that gives us an estimate of how many satisfying assignments there are. Now, we need to do the confidence, so we need to iterate it several times to get the desired confidence. And this gives us a solver which we call ApproxMC, and it's polynomial relative to a SAT oracle, of course, but polynomial in the side of the formula in 1 over epsilon and in 1 over log 1 minus delta. So, so you want higher confidence. It depends on what level of confidence you want. More accuracy, it will depend on how much accuracy you want. So again, let's compare it to Cache. Was when we came up first, Cache was the best exact model counter. And so we chose epsilon to be 0.75, which we allow error of 75%. But amazingly, we discovered that ApproxMC was within 5% of the correct answer. Cache give you the correct answer. And even though we allow ourselves an error of 0.75, we never got an error larger than 5%. So it's actually, the approximation is very, very good. In fact, it's better than what we predicted. And this still, it's an interesting question. It just means that our theoretical analysis is not tight enough. One should be able to get tighter analysis on the accuracy. In terms of performance, the answer is more nuanced. So for small benchmarks, up to, let's say, 50,000 variables, our approach has too much overhead, and Cache would be much faster. But once you go to larger benchmark, Cache just times out. I mean, in general, we saw that if Cache does not give you an answer in 5 minutes, it will never give you an answer. And in contrast, ApproxMC were able to scale it up to hundreds of thousands of variables. So really, you want to combine the two things. You want, on small benchmarks, you want to run Cache. On large benchmarks, you want to run ApproxMC. So let me go back to neural nets, where we kind of started it, deep learning. And Kuldeep Mill, who was my student and then went on to work with other people, show how to use approximate counting for analysis of neural nets. They look at security properties of neural nets, and they want to get quantitative answers. They want to get some, again, to define some notion to say that, and I'm not going to define robustness, resilient to Trojan attacks, fairness, all of this. We want to get quantitative answer. How good is it? Can I say that with 90% or 99%, it's going to be robust, it's going to be resilient, all of this stuff. And they show how for a whole class of problem over neural nets, you can use ApproxMC to get quantitative answer about the quality of deep learning. So I think that's an important part. You can look at it as not exactly explainable AI, but it gives you some measure of confidence in neural nets. So let me kind of try to finish by reflecting on the story here. So one is that it's important for everyone to know that while we had revolutionary progress in machine learning, in deep learning, we also had revolutionary progress in such solving. And I think the biggest mistake that people in the area did was to call it CDCL solvers. It's horrible marketing. They should call it deep solving. Whoever came up with the term deep learning, of course, deep learning was a number of layers, but if we had called them deep solving, I think then there would be much better, much more well-known appreciation of the progress in automated reasoning. The other message that I want to send here, that having this such powerful such solver is an amazing enabler. And I gave here just two applications of approximate sampling and counting, what you can do using such solver as a black box, essentially. But there is a general rule in mathematics, in science in general. When you have a big hammer, go look for nails. And I would like to encourage all of you to think, how can you use, this is today such solver, a big hammer. How can you use it on your own research, leverage the success of such solving? Now, clearly, I don't want to say that SAT is an easy problem now. SAT is a challenging problem. and sharp-sat is even more challenging. And scalability is an ongoing challenge. And Kuldeep Mill graduated from Rice in 2017 and went on to do good work in the area. And by now, I've lost count. I think he maybe have by now ApproxMC4. He's continue to be able to improve the ApproxMC, and UniGen the same thing, to make it scale better and better and better. It's always about scalability. If you think that's not good enough, well, Moore's law was always just all about scalability. And finally, let's reflect a little bit about, we've kind of always assumed that P versus NP is a central question in theoretical computer science. But when I was a freshman in physics, one of the TAs asked, what's the difference between theory and practice? And we couldn't give him the good answer. He said, in theory, they're not that different, but in practice, they're very different. So P versus NP is a beautiful theoretical question, but in practice, not clear that it has implication. Okay, it could be that P equal NP, but algorithms are not useful because it's like n to the 1,000, which is a useless polynomial. It could be that P is not equal in P, but you can solve everything in NP in n to the log n. And so in practice, it will run well depending on the constant. So while it is a beautiful theoretical question, there's no guarantee that it will have practical benefit. And so we kind of still teach students, if NP-complete problems are hard. Are they really hard? When I was taught, you see NP-complete problem, think of it as something that's about to explode. Stay away from it. Don't even get close. Who knows what will happen. But we show that NP-complete problems are sometimes hard, sometimes not hard. And complexity theory that was supposed to tell us what is hard, what is not hard, has failed to deliver on that. The saying SAT is NP-complete, they don't explain why some SAT problems are hard and some are easy. And we even have a new notion of what it means to have an effective algorithm. BPP to the NP, which is the random polynomial time, with a SAT oracle. Maybe we should call this the new P time. So there are more things to think about. And concluding on the questions of model-driven science for back to data-driven science, I think it's a paradigm glide, not a paradigm shift. As I said, data science, driven science, refined model-driven science does not replace it. As I said, physicists still use classical physics, but if we want to have a human-centered AI, I think bridging machine learning and logic is one of the central challenges. And I'll close with that. Thank you very much.
Thank you. Thank you, Moshe. So I think we can start asking some questions. So please write questions in the chat. I don't know whether we would like to start with asking Marco, Giuseppe.
So I don't see a chart, so I guess
you'll ask me. Yes.
Yeah, you'll ask me. I don't see the chart. Yeah.
Marco.
Okay. Thank you for the wonderful presentation, introduction. Basically, so in the history of your presentation, you showed that basically SAT and SMFE at some point got into production, got into market. So they were used to solve real applications, right?
They're being, go to a small software company that you have 5 people started with a startup and say, are you using such software? The answer will be probably not.
Okay.
But in a large, sophisticated company like Microsoft, in a company like Intel, large companies that can afford to build deep expertise, it's today part of the development practice. I think it's just a matter of time before there will be tools that will be popular enough that small companies the point is, you still need expertise to use these tools. They're not off-the-shelf tools, so to speak. Okay.
Thank you. So we have a question from...
I'm cool.
Okay. So Marco, continue.
No. So I'm curious, just a curiosity. If you envision other problems on language or tools logical problems in regions that are close to go to market. I don't know, Cusat, for example. You know that in Genova we have been working a lot on this.
So you have. I mean, think of SAT now as what maybe linear programming used to be. So now you think of linear programming as it's a general problem-solving framework. What the SAT community has not done yet, which the linear programming community or the OR community has done, they understood that having a solver is not enough. You need to allow people to phrase the problem. They need tools how to take some other problems and pose it as linear programming. So they have built modeling frameworks. They have built frameworks where it's a modeling framework. It's not, you don't have to sit down and write linear inequalities. Okay, you build a model, and that model you tie to a linear problems LP solvers. And the closest we have for this, I think, in computer science is answer set programming. If you look at the success of answer set programming, it was really, the idea was before SAT solvers. People came with the idea of answer set programming, but it couldn't deliver because the problems were hard and they didn't have good solvers. Once you hook answer set programming to SAT solver, it's a very good tool. I don't know, it's an interesting question why answer set programming has not become more widely known. Maybe it's an issue of education. If today, I think if we teach, you teach AI course, I think we should teach now, we should teach answer set programming. It's part of the basic tools of AI. Well, it hasn't happened yet. Okay.
I'm doing it.
You're doing it. Wonderful. I think, it's just, we always talk about tech transfer. And the answer is the best way to do tech transfer is teach it to your student. Because most of your students will go to work at the industry, and whatever they learn in college, they think, oh, this is standard stuff. I learned it in college.
Thank you, Moshe. I completely agree with you, by the way. Thank you.
Okay, Moshe, some question here from the chat. Italo Oliveira, may you indicate some of the best current SAT solvers?
So the best way to find the best current SAT solver is just run a web search, Google on a SAT competition and the annual competition. And I mean, I haven't looked exactly which are the SAT solvers that came on top, but it's a competitive area. There are people there and they are making still amazing progress every year. And that, to me, if you want to know what is the best SAT solver, just look at the SAT competition. What is it going to be this year, 2022? Find out which are the best SAT solvers.
Okay. So, other questions. Luciano Serafini. So, can you say something more on how weighted model sampling could work?
Okay. So, when I talked about sampling, I assumed that I said it was uniform. But in reality, uniform in many applications, uniform is not good enough. You want to weight. For example, even in random constraint verification, you want to say which areas are more important than other areas. So there are ways to do that, and we have one of the things that we have looked at for model counting and for sampling is one of the simplest models. There are more sophisticated models, but the simplest model is called literal weight. So literal weight, you say, okay, take a P0. If it's true, I'll give it this weight. And if it's false, I'll give it another weight. In some application, they sum up to 1. The two things that sum up to 1. In some application, not necessarily. But then you take a full assignment. You take the product of all the literal weights. That's the weight of a single assignment. And then the count is the total sum of all the weight. This is also weighted, called weighted sharp SAT. And there is also a development on both exact model counting and on approximate model counting, how to handle weights. And I said the popular model of weights is literal weight, because it's relatively kind of clean, mathematical clean model. There are more sophisticated model how to define weights. But we have looked mostly at literal weighted counting and sampling. There's been lots of progress on that too.
Okay.
I mean, I had to sit last night, guys, and chop my 1 hour talk to 40 minutes, painfully, you know.
So Giuseppe, where you do you want to post some questions? We have others in the chat. In any case, let's start from the chat first. We have Carlo Adornetto. Do you think SAT can be applied in the context of imaging with convolutionary neural networks? And about the example of security, what kind of neural networks you were referring to?
So I have this kind of grand idea that will take a while to go there. But part of the problem is let's take you use CNNs for imaging, okay, to decide if something is cancer or not, okay. How accurate is it? It tells you this is cancer, okay. How accurate is it? How much can we trust it? And you know, and we talked before about safety of AVs, and we say if you really want to do just purely data driven, then you'll have to drive billion miles, test drive billion miles to get the level of safety that's needed. How do we guarantee the safety of CNN's prediction, classification? That's what they do. They're one of the key application classifier. So people have tried to develop connection between CNNs and graphical models. But now you need to do probabilistic reasoning on very large graphical models. It's beyond the state of the art. And so one of the questions is, can we take some of this technology and using, for example, idea that we can do approximation and get scalability and apply to large probabilistic models, which then will be connected to deep neural networks. So this is kind of I would say is a kind of grand challenge that I have in mind, and part of trying to build the underlying technology, and that's why we're focusing so much on scalability. The same way that SAT for many years was they made progress, but the industry was laughing at them. They said they're solving 1,000 variables. We need million variables. Well, by the time they were able to solve million variable, people in the industry says, give it to us. Now we're ready to use it. And so for many years, they were just laughing at the academics, but if the academics kept making progress, eventually it reached industrial applicability. So that's the hope, that we will scale this technology and to the level it is industrially applicable. Kuldeep Mill recently gave talks. He was in job market, he gave talks and he asked me for comments. And he said, people will say that I'm working on the same problem now for 10 years. And what have you done? You're working on the same problem. And I says, scalability is a holy grail in computing. You know, we look at the whole idea that we said for many, many years, we rode on Moore's law, was just about scalability. Being able to scale is always requires innovation and cleverness and engineering. I mean, it's a whole bunch of things. Lots of stuff goes into just how to scale performance. That scalability is a noble pursuit. Don't be embarrassed about saying I spent the last 10 years pursuing scalability. Perfectly okay. So we are not there yet, I would say, for much of these technologies. We are in the case of probabilistic reasoning, we're not there yet for industrial application.
Thank you, Moshe. Here we have Arash. Could you talk a bit about other important problems in connecting logics and machine learning?
So, I mean, there are kind of some of the other things that other people are working on. I worked a little bit on that. Was can we train machine learning to do reasoning? So we assume that reasoning is kind of classical algorithmics. What does it mean? You and I look at the problem, we think very hard, we come up with an algorithm, we prove its correctness, and then we come up with heuristics. This is what I call traditional algorithmics. That's the approach we've been using in algorithm since actually, I don't know exactly when it started, when even Euclid's algorithm kind of, here is the problem, find an algorithmic way of solving it, then we start analyzing runtime, etc., etc. Now people are asking, well, can we just do supervised learning at least? Can we train some neural net on small problems and then use it to solve large problems. So, and people asking it specific for automated reasoning, but also for combinatorial optimization in general. So a few years ago, Luis Lam from Brazil, my colleague in Brazil, and I looked at it and I said, no way we're going to be able to use deep learning for combinatorial optimization. I don't believe that this is going to work. Let's write a paper showing that this doesn't work. And we decided to look at, what did we look at? We look at TSP. And then we start doing it. I said, we're going to write a paper that debunking. I said, it's time to debunk the enthusiasm of deep learning. To our surprise, it worked fairly well. Now, it doesn't offer any guarantee. It's kind of a best effort. But, very often in combinatorial optimization, you don't need a guarantee. We just said, this is the solution I can give you, okay? You decide if it's good enough for what. You want to find out, is there a route for the traveling salesman that will do this? This is a solution I found. You decide if it's good enough or not. I can say nothing about optimality. But it's actually performed fairly well relative to optimal solvers. So this is to understand this whole connection between, in particular, people look at GNN, graph neural nets, for maybe learning algorithms on graphs. This is so it's about logic, but it's even more broadly trying to look at the same issue. We have this new paradigm of data-driven, and we have the older paradigm, how we design algorithms. Can we bridge these two paradigms? How do they live together? And this partly, the phrase neurosymbolic reasoning means different things to different people. But more and more you hear people that says that if we, instead of being arrogant and to say, throw away the old stuff, we have now the new stuff. Everything we learn in symbolic reasoning, in symbolic AI is useful. Let's leverage it. Everything we learn in probabilistic reasoning is useful. Let's have a grand unification where every time we saw the amazing power of neural nets to learn from big data, but let's combine everything we know and do it together. But how to do it well, that's very much, I think, is a part of the frontier now in AI.
Many thanks, Moshe. Maybe just one further question. Maybe Giuseppe was waiting.
No, I was only mentioning about SAT. That SAT is a little bit like an assembler language for problems. So we need somehow high-level language, close to humans, in order to.
No, I completely agree. I said that if you look at people in OR, people in industry that use LP, they don't sit down and write inequalities. Nobody would do that. This would be like not even assembler. This would be like writing in machine language directly, in opcodes, in hexadecimal. Nobody would do that. That's why I think that the closest that I see now is answer set programming.
Right.
And I think it's on us to popularize it. And there is a question, how good is it as a problem solving environment? And that's partly not just a technical issue, that's a user interface issues. And so we need to get people involved on it and try to, I think this is right now our best answer, how to use kind of propositional logic to really solve problems is answer set programming. I will be happy to learn about other ways to do that. But I think right now it's the most promising answer.
Okay, many thanks, Moshe, for your great talk. Many thanks for having accepted our invitation. So,
Grazie mille.
So, this is our last seminar in this spring series. So, with Moshe, we concluded this series, but before concluding, I would like to thank Giuseppe De Giacomo, Marco Maratea, and Chiara Ghedini, who helped me in organizing this novel initiative of the Italian Association of Artificial Intelligence. And we will start again with the autumn series. So let's see all of you in autumn. Bye.
Ciao. Arrivederci.
Bye.